Hello students, welcome to my YouTube channel Data Shah. In this lecture we'll be talking about the two-phase method. In the previous lecture we have discussed the simplex method and its examples. So simplex method is of two types. The first one is when we are having the constraints with the less than equal to form. So we use the normal simplex method. When at least one of the constraint is greater than equal to or equal to form, then we are using the two-phase or the big M method. So in this lecture we are discussing two-phase method with a few examples. So as the name suggests, two-phase method means that it is having two phases. In the first phase, we'll be finding the initial basic feasible solution to the original problem, and we'll be defining an artificial objective function which is created with the help of the sum of all the artificial variables. So the new objective function is subjected to the constraints that is given with the original problem, and we'll be solving using the normal simplex method. Now at the end of the phase 1, three cases arise. If the minimum value of z star is equal to 0 and at least one of the artificial variables appear in the basis at a positive level, at least one of the artificial variables at a positive level, then the given problem has no feasible solution and the procedure terminates there. Second case, if the minimum value is equal to 0 and no artificial variable appears in the basis, so a basic feasible solution is obtained, so we move to the second phase. Third case, if the minimum value is equal to 0 and one or more artificial variable appears in the basis at a 0 level, then the feasible solution to the original problem is obtained and we can move to the second phase. So in the second phase, when the last two cases arises, only then we can move to the second phase. So in the second phase, we have the normal simplex method, and we could solve the problem and find the optimal solution. So let us consider one example. Solve the given LPP by the two-phase method. So in this, the objective function is of the maximization type, subject to the three constraints, and we are given that x1, x2, x3 are greater than equal to 0. So as this is equal to here, so we'll be adding an artificial variable, and these two are less than equal to constraint, so we'll be adding slack variables. So in the phase 1, as you could see here, the constraints are 2x1 plus x2 minus x3 plus a1, where a1 is the artificial variable and S1 and S2 are the slack variables. So the phase 1, the most important part in the phase 1 is that we'll be defining the auxiliary LPP with the objective function. So we are defining the new objective function as maximize z star, where the cost of x1, the decision variables are 0, and we are assigning a cost of -1 to the artificial variable and 0 cost to the other variables. So 0 cost to S1 and S2 as well. So where all the decision variables and A1, S1 and S2 are greater than equal to 0. So this is our auxiliary LPP. So how we could solve them? We'll be applying the same simplex method. So this is our initial table, and as you could see here, let me just write the CJ. The x1 0 0 0. This is also 0, and this is -1. So as you could see here, the cost in the basis, the objective function, we are having -1, 0 and 0. Now what is XB? XB is the basic solution that we get when we put the decision variables equal to 0 in all these three equations. So when you put x1, x2, x3 equal to 0, so we will get A1 is equal to 20, S1 is equal to 76, S2 is equal to 50. So the same we are having here in the XB. Now the coefficients of the x1 and x2 in these two columns, x3, and the coefficients of s1, s2 and a1, as you could see. So the same process we'll be following. We'll be finding out z. So here we are getting z star as minus 20. So we'll be calculating zj. Zj would be minus 2, minus 1, 6, 0, 0, 1. So delta j, that is zj minus cj. So we could calculate the value. So we are getting this as minus 2, minus 1, 6, 0, 0. So 1 plus 1 is 2. So as we could see here, minus 2 is this. So this is the most negative. So this would be the entering variable in the next iteration table. So the minimum ratio would be selected in the similar way as we have done it before. So 20 divided by 2, that's 10. 76 divided by 6, 50 divided by 8. So as we could find out, this would be the minimum ratio. So this would be the leaving variable in the matrix. So x1 will be the entering variable and s2 would be the leaving variable. So the pivot element is denoted by this. So that means in the next iteration table, we'll be having a1, s1 and s2 will be leaving. So x1 will be entering the basis. So the cost remains same, minus 1, 0. x1 would be again 0. So as 8 is the pivot element, so we'll be dividing the whole row. Row 3 goes to row 3 divided by 8. So we'll be having here 50 by 8. This is 1 minus 3 by 8, 6 by 8, 0, 0, 0. And the rest of the elements that we have above 8, we have to make them 0. So how we can make them 0? So R1 goes to R1 minus twice of row 3, and this would be row 2 goes to row 2 minus 6 times of row 3. So let's just subtract it. So this is 20 minus 2 times of 50 over 8. So we'll be getting this as 4, 25, 2. So 40 minus 25 by 2. So we are getting it as 15 over 2. So this is this becomes 0. So this is 1 minus we are having this as plus 3 by 4. So this is 7 by 4. So this is minus 6 plus minus 6 over 4. So this is minus 6 12, 15. Over 2. So this is 0, 0. So 1 minus is 1 only. The next that we are having is R2. I'll just erase this. R2 minus 6 times of R3. So to make this 0, so this would be the first one 76 minus 6 times of R3. So we'll be getting this as So this would be, so here I'll be getting the answer as 77 by 2. This would be 5 minus plus 6 3s are 18 by 8. So 9 by 4, 29 by 4. Next would be on the similar pattern, 10 minus 6 times 6 over 8. So that's 3, 3. So 10 minus 9 by 2, 20 minus is 11 by 2. So that's 1, 0, 0. So this is what we are getting. So quickly let's calculate Z star. It's coming out to be minus 15 by 2. Zj would be 0 in this case. This would be minus 7 by 4, 15 by 2, 0, 0, that's minus 1. So delta j, zj minus cj would be the same, as we could say 0 minus 0. This is minus 7 by 4, 15 by 2, 0, 0. This is again 0. So what we have observed here, so as this is the most negative, so this would be the entering variable, and in this entering variable we'll be calculating the minimum ratio. So x2 will enter. Now what will leave, either a1 will leave or s1 or x1, we have to decide. So x1 cannot leave, and we cannot find the minimum ratio because this is negative, so we'll be just ignoring this one. So this would be 15 by 2 divided by 7 by 4. So this would be 4.28 when we'll calculate, and this would be 77 by 2 divided by 29 by 4. This is coming out to be 5.31 when we'll calculate. So this would be the leaving variable. So this is our pivot element. So we could identify that at the end of this phase, when we'll be doing the next table, in that we'll be x2 would be entering the basis, and a1 would be leaving the basis. So a1 would leave, so x2 is entering. This is s2, x3, that was x1. So the cost is 0, and as we have the pivot element, so need to make it as 1. So we have to divide the whole row by 4 by 7. So we'll get this. So I'll quickly write the answers. So now as the artificial variable has been deleted, gone from the basis, so we can exempt this column as well. So there's no need to write the values. So here after the elementary row operations, we'll be getting for row 2. For row 3 we'll be getting 7.85, 1, 0, minus 0.86, 0, 0.073. So Cj would be, this is minus 1, and Z star we are getting it 0. Zj that we are getting is again 0 in all the case. Delta j would be 0. So as we could see that at the end of the phase 1, Z star is at a 0 level. As we know, Z star is at a 0 level with no artificial variable in the basis. That means here we can't see any artificial variable. So that means we can move to the second phase. So the second phase, when we'll be considering, we will have the objective function, the first objective function that was given to us in the question, 5x1 minus 4, this is x2, plus 3x3 plus 0s1 plus 0s2, and we'll not be considering the artificial variables here, and this would be the normal simplex method that we'll be following. So let us fill the values here. So Cj would be 5 minus 4 3 0 0. This would be the cost that is given to us. So 5 minus 4 3 0 0. So now in the bases we have x2, s1 and x1. So their cost. Now the rest, everything would be copied from the previous table. So as we are having here 4.28, 7.47, 7.85, so I'll be taking all these values and everything that is written here, I'll be just carrying it forward to the next iteration table in the phase 2. So just copying it quickly. So this is 0 0 1 1 0 0. So this is minus 4.28, 36.53 minus 0.86 0 0 0. So this is 0.073. So let's calculate. Now we'll be calculating the Z value. Z would be when you'll multiply these two, minus 4 into 4.28 and plus 5 into 7.85. So we could calculate this value. So till the time we can calculate Zj. Zj would be 5. This is minus 4. This again we can calculate using this. So this would be 0. And this is coming out to be 12.82, 0.925. Now Zj minus Cj, so let me just write delta J. So Zj minus Cj is 0, minus 4 plus 4 is 0. So this is 12.82 minus 3, that is 9.82, 0, 0.925. Now as we could see here that all as the delta J is greater than equal to 0, and so we have the optimal solution in phase 2. So in the initial table of the phase 2, you are getting the optimal solution that is given by x1, that is 7.85, that is written here, x2 as 4.28 and x3 equal to 0. So when we'll calculate Z, that we are getting maximize Z, that is 5, 7.85 4, 4.28 plus 3 into 0, this will give us 22.15, and when you'll check this is also coming out to be 22.15. So this is our maximize Z. So this would be the answer in this case.